Okay, so here we go with the second question from the 2017 C3L6 paper. Now, I ought to warn you straight off that this is definitely the side of the course that I know less well, and I'm never as good on these second questions as I am on the first ones. So I'll probably be a lot more hesitant and shaky than I was on the first question, but here we go. Drugs made from bromoalkanes. Bromoalkanes are useful starting materials for the synthesis of drug molecules. In some cases, the required bromoalkanes can themselves be made by the reaction of alkane with bromine. For parts A to F in this question, you can assume that only one hydrogen atom in each alkane is replaced. Okay, that's probably going to help us here. 1 mole of ethane reacts with 1 mole of bromine to give bromoethane. Write a balanced equation for this reaction. State symbols are not required. Okay, C2H6 plus bromine gas forming C2H5Br. What happens? Well, we also generate hydrogen bromide. Fairly straightforward starter. How would you classify this reaction? It is a substitution reaction. What we're essentially doing is we are substituting one of these hydrogens for a bromine. So we're substituting that hydrogen for that bromine. We're not adding more, we're substituting one thing for another. The reaction between the ethane and the bromine requires light and does not proceed in the dark. The light needed to break the bond to start the reaction, which bond is broken by the light. You may or may not know that actually is this weak bromine-bromine bond that is broken by the light there, generating bromine radicals. When ethane reacts with bromine, any one of the 6 hydrogen atoms can be replaced. The symmetry in the molecule of ethane, that means all 6 of these hydrogen atoms are equivalent, so there's only one possible product, no matter which hydrogen is replaced. But with larger alkanes, there's often the possibility of forming different structures of the bromoalkane product, depending on which hydrogen atom is replaced with a bromine atom. For example, when we do this reaction with methylbutane, we end up with 4 different bromoalkanes. Assuming the hydrogen atoms present are equally likely to be replaced, which of the bromoalkanes would you expect to be formed in the smallest proportion? Okay, so we've got 1, 2, 3, 4, 5, 6, which would lead to A. So if I just mark these as A, that would give A. So there's 6 ways that we could get A. There's only one hydrogen which would lead to B, so there's only one way we would do that. I've given too much here. For this one, there's 2 ways, so C, so there's 2 ways we could get that way, and there's D. Any of those could be replaced. So there are 3 ways to get that. So the one that we get in the smallest proportion would be B, and we've got to give the systematic name of this bromoalkane. Well, it's based on 1, 2, 3, 4, so it's based on butane, so I expect it is 2-bromo 2-methyl-butane. Using the same assumption as in part B above, calculate the percentage of the 4 products that you would expect to find in the mixture. Okay, well there are 9 hydrogens, 10 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. Okay, so A would be 6/12, which is 50%. B would be 1/12, which is 8%. C therefore would be 17%. And D would be 25%. I'm not sure if that, yeah, that does actually add up, doesn't it? D is 3/12. Oh, of course it is. 25%. Yeah, I can do that. 25%. Calculate the percentage of the 4 products. When this reaction was performed in the laboratory, the actual ratio of products observed to the nearest 0.1% was as follows. Okay, so that's not what we'd expect. B actually turns out to be the most likely product. To determine which position is most reactive under these conditions, i.e. the preference of any particular hydrogen to be replaced, we have to compare the ratio of the percentage of each product actually produced with that predicted. This gives a measure of the inherent reactivity of each position. What is the relative reactivity of replacing a hydrogen to form compound B compared with replacing a hydrogen to form compound C? Okay, so the reactivity of B seems to be something like 93.5% divided by what we'd actually expect, which was 8.33%. So how many times more likely is that? 93.5 divided by 8.33. That is about 11.2 times more likely. Whereas for C, we expected 17%, or 16.66, and we actually got 6.3%. 6.3 divided by 16.66% equals 0.38 times as likely. So I'm presuming that what I do is I compare those number there, 11.2 divided by 0.38, and say it's 29 times more likely. That's my best guess as to what that means. By considering the symmetry of the following alkanes or otherwise, determine how many different bromo-alkane structural isomers could be formed by the replacement of one hydrogen atom with bromine. Okay, so for one, we've got, they would all be the same. So that's 1, 2, 3. So there'd be 3 there. All these positions are absolutely identical. So there would only be 1 there. These positions are identical, and if you're not sure how I'm doing this, I'm looking for lines of symmetry. So I can see symmetry in the molecule there and there. So those are all the same. These 4 positions are all the same, and there's a hydrogen here, so again I think that would be 3. For this one, these are all the same, 1, 1, 1. There's a hydrogen there, 2, 3, 4, 5. So I think that would give us 5 different ones. For this, there is symmetry down the middle of the molecule that way. There's also symmetry down the molecule this way. So that 1, 2, 3, 4 are identical. That's 1. That and that are identical, 2. And then that is 3. Now, I've seen this molecule before, so I know that this is a trick. That position there is actually the same as this position here, and this position here. Whether you can see that or not without building a model, I don't know. But if you follow it through, each one of those has a hydrogen pointing out and 3 things that then go on to another equivalent position. So that's 1, and then there's 2, 2, 2, 2, 2, 2. So that actually only would give you 2 different structural isomers. Memantine is one of the only drugs available to help lessen the symptoms of diseases such as Alzheimer's. The synthesis of memantine begins with the bromination of 1,3-dimethyladamantane to form compound E, which replaces a single hydrogen atom with bromine. How many different structural isomers of the bromoalkene E could be possibly formed by replacing one hydrogen with bromine? Okay, so clearly that and that are identical because there is certainly symmetry down the middle of this molecule. I'm trying to work out whether or not that and that are identical. I think they are, aren't they? So that's 1, 2. I think that's its own unique environment. There's no hydrogens there or there, okay? I almost fell for that, but there's no hydrogen, so 2. 3 is that one, is that one, and is that one. I think they're all the same. 4 is that one, and that's 5. So I think there's 5 different hydrogen environments in that particular molecule, and that's basically taking that there is this line going through those 2 carbons there, so that the top and bottom and left and right are the same in each case for that, I think. So I think the answer to that is 5. In the synthesis of memantine in the laboratory, only one structural isomer of E was formed. By considering the information earlier in the question, draw the structure of this isomer, add the bromine to the framework in your answer booklet. So presumably we've got this drawn in the answer booklet here. Okay, so information earlier in the question. So looking up here, clearly what we like is the fact that the tertiary carbocation is the most stable, or the hydrogen that's attached to 3 other carbon groups. That was the most stable one by far. Followed by the secondary, so this one attached to 2 carbon groups here. And again, I'm not sure I'm using the terminology correctly here because I'm not an organic chemist, but then primary. So we're looking for anything where there's a hydrogen that is only attached to, and I think this one here, isn't it? Because there's a single hydrogen here, whereas here, oh, sorry, what have I done wrong? Ah, that goes up there, sorry, and then that goes along and down. Okay, let me get rid of that. Oh dear. Okay, anyway, so let me try and correct this drawing down here, and then that comes there and there. This here, I think this would be the hydrogen that would be removed and turned into bromine. That's my best guess based on the fact that it seems to be the carbon, the one that's attached to 3 other things, no other hydrogens. So that was that question. Lost my pen again. There. The conversion of E into memantine requires only 2 more steps. The first of these steps is achieved in a reaction called a Ritter reaction. In the scheme for this reaction shown below, the letter R represents any alkyl group, and this is really common, okay? R is the boring bit of the compound that we're not interested in. So we take the R, we add cyanomethane actually, sulfuric acid, water, and we get this. And then the conversion of E, we do that, we get compound F, we get sodium hydroxide, and then we get memantine plus sodium plus G. Okay. By modifying the structures shown in your answer book, show the structures of compound F, memantine, and anion G. Okay, I'm going to have to do this myself because I haven't got the answer booklet to hand. Okay, so we said, didn't we, that this was going to be the bromine, and clearly what this does is it swaps the bromine for an NHCO like that group. Okay, so that is compound F there. Now memantine, are we told what memantine is? No, we don't know what the structure of memantine, we've got no information about that. Okay, so sodium hydroxide, what's that going to do? My best guess is it's going to hydrolyze this amide here. So hydroxide will be attacking the very positive carbon there, and will that be turning that into an amide? So up, down, kicking that out, where it'll pick up a proton from the water, something like that. So my best guess, and I don't know how much you've already done in organic chemistry, is that you've got this R group here, and that's going to generate NH2 and methanoic acid. That's my best guess here. Oh, except it generates sodium. Oh, okay. And anion G. In which case, so I'm sure the hydroxide is coming in and attacking that carbonyl group, because that's really positive, right? The question is what's going to happen over that. I'm sure it's going to hydrolyze this amide bond, because I know that amides hydrolyze in alkali. It's possibly sodium obviously comes from the fact you've got this sodium hydroxide, right? NaOH. So it could be, yes, that would, of course, that would deprotonate in high pH. Of course it would. So the anion would be the carboxylate anion there. So that would lose its proton. It's an acid, it will lose its proton. So that would be the carboxylate anion. Presumably that is memantine, and then you've got sodium. That's my best guess now, okay? Oh, relative molecular mass of 59. Oh, that would have helped, wouldn't it? So let's just check that. What would that be? That would be 12, 12, 16, 16 plus 1, 2, 3, another 3, 24 plus 32 plus 3 equals 59. Good, yeah, I've got it. Right, there we go. Okay, that was right. I missed that bit. The drug carpipramine is used for the treatment of schizophrenia and anxiety. The synthesis of carpipramine uses 1,3-dibromopropane as one of the starting materials. Draw the other structural isomers of dibromopropane. Okay, so let's do it on the left for once. Propane. You've got 3. Let's see. So you've got 1,3-dibromopropane. You could have 1,1-dibromopropane. You could have 1,2-dibromopropane, and presumably you could have 2,2-dibromopropane. 3, 3 is the same as 1, 1. 3, 2 is the same as 1, 2. I think they're probably it. So I think there's 3 more isomers of 1,3-dibromopropane. If 2 moles of bromine are added to 1 mole of propane and then the mixture is subjected to light, a mixture of these dibromopropanes can be produced. Calculate the percentage of 1,3-dibromopropane that would be produced in this mixture if all the hydrogen atoms were equally likely to be replaced in this reaction. Oh gosh, they do like difficult questions, don't they? Right, so we got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the chance of the first one going on the end, either end, is basically 6 out of 8, right? So that's the chance that the first one so the first one, if all equally likely, the chance that the first one would go on the end position is 6 out of 8. Now, having got that and replace one of these with bromine, the chance that the next one would go on the other end is 3 chances out of the 7 remaining. The 7 remaining hydrogens, okay? 3 there, but you've got 2 there and 2 there, so 3/7. So I think the chance, or the percentage of it, would be 6/8 times 3/7, which is 32%. And again, I might be horribly wrong here, and the mathematicians might be screaming at me, saying I've made a really obvious mistake. But to me, it seems that should be about 32%. Unfortunately, no 1,3-dibromopropane is produced at all when this reaction is attempted in the laboratory, as the reaction favours other isomers. However, another hydrocarbon, H, does react with bromine to give 1,3-dibromopropane. The hydrocarbon contains 85.63% carbon by mass, and when it reacts with bromine it gives no other products other than 1,3-dibromopropane. Draw the structure of H. Okay, so in 100 grams, 85.63 grams of carbon, meaning, I should be able to do this in my head, but I'm feeling lazy. It's 14.37 grams of hydrogen. Divide that by 12, divide that by 1. That's obviously 14.37. 85.63 divided by 12 is 7.14. I'm going to basically just assume that that is a 2-to-1 ratio. Can I do that? Yeah, I'm just going to assume that's a 2-to-1 ratio. Right. So clearly, given that alkanes are CnH2n plus 2, either this is an alkene or it's cyclic. Now, the problem, I think, if it was an alkene, is that it would go on to adjacent. Oh, is this right? Am I right? How would you classify the reaction? What if we had this, okay? Cyclopropane. And then the bromine substituted in these two positions. No, it didn't. It added there. Could that work? Could that split it up? In fact, if it added here, right, sorry, yeah, if it goes in here and it breaks this bond, and you add a bromine there and a bromine there, that would give you 1,3-dibromopropane. So what would that be? Well, that's now not a substitution reaction. not hydrolysis, we're not using water, it's not cracking, it's not polymerization, it's not elimination, so it must be an addition reaction. I reckon that's what's going on. The synthesis of carpipramine is shown below. That plus that 1,3-dibromopropane, compound I, reagent J, which is a base. Draw the structures of compound I and reagent J. Okay. Right, I'm presuming what's happening here is that the lone pair on that nitrogen is attacking that carbon and kicking bromine out as a leaving group there. So I suspect I, and if you'll forgive me with calling all this sort of just a sort of random C so I don't have to draw it, nitrogen, nitrogen, 1, 2, 3, because that's 1, 2, 3 carbons we're adding, bromine, and that's what I is. And that just represents the rest of that group. Okay, I just can't be bothered to draw it. And then reagent J, I'm guessing must just be this with a hydrogen on it. So something like nitrogen, NH, nitrogen, 1, 2, 3, 4, 5, 6. And then that can obviously attack in to the other side and kick out the other bromine there. And that's how you join these two nitrogens, will be joined where the bromines were originally. So we've just linked this group, this nitrogen and this nitrogen together via that 3-carbon chain. 1,3-dibromopropane is also used in the synthesis of the drug ethoheptazine, used to treat pain and anxiety. The synthesis is shown below. The carbon atoms in ethoheptazine, which are not already present in the starting material, either come from 1,3-dibromopropane or from ethanol. No carbon-carbon bonds are broken during the synthesis. Oh, this is going to be difficult, isn't it? I'm already dreading this question. In the answer book, circle the 3 carbon atoms in ethoheptazine which come from 1,3-dibromopropane. Right. Let's presume that this ring here is this ring here. This nitrogen here is this nitrogen here, okay? So that's what I'm guessing. So from this to that nitrogen, we've got 1, 2, 3, 4 bonds. We've got 1, 2, 3, 4 bonds to that nitrogen. We've also got 1 extra carbon here, but then we've got 3 carbons sitting in here. So I'm suspecting these 3 carbons here are the ones that are added from dibromopropane, okay? So I'm pretty certain that's right, because if we go 1, 2, 3, 4, 5, that's too many bonds, 1, 2, 3, 4, between that and that nitrogen. So I'm guessing that cyano group actually becomes this bit down here. And so it's those 3 carbons there that somehow get added on between that and that. In the answer booklet, circle the 2 carbon atoms in ethoheptazine which come from ethanol. That's much easier, isn't it? So that is these 2. So that's ethanol, isn't it? OH clearly having come in and attacked something. So that we're okay with. In fact, I better not tick it, because I'll do that later. So that's those. The synthesis of ethoheptazine takes 5 steps. In the first step, the starting material is deprotonated to give K-, which is a carbanion, i.e. an anion in which a carbon atom has a negative charge. Draw the structures of the carbanion K-, compound L, carbocation M+, and compound N. Oh, nice and easy, hey? Right. If we think about what the first part of the question was trying to show us, it's where these bromines are going, and there's often a link back. So these bromines, we were saying, were going where there's a tertiary carbon, and all the way back to here with B, they're indicating that actually the things that are easiest to remove, the carbocations probably, are the ones which are most stable. So looking at this, my best guess is that you are pulling off a hydrogen from here. That's what you probably are doing. So that you need a carbon with a negative charge. So let's say this is what it looks like. Minus charge on that. Now, why else did I pick that other than its tertiary? Well, I know I've got to somehow join that carbon up with this nitrogen via, look, there you go. Here, I've got to join that carbon up with that nitrogen via the bromine thing. So I really do want somehow this to be reactive. So let's put together that with what we saw at the start of the question, and we'll pull off that hydrogen. So that's K-, let's say. The next thing is we're adding this 1,3-dibromopropane, and it asks us for compound L. So let's say that just attacks in 1, 2, 3, bromine. So that attacks in there and kicks out the bromine. So the next thing will be, I'm starting to regret this question completely. 1, 2, 3. So that will be attached to 1, 2, 3 carbons and then a bromine like that. So I reckon that's what compound L looks like. It says heat this for a while, and we get cation M+, and bromine formed. Okay, so clearly something's going to attack that. Cation M is C15, so let's count the carbons. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So clearly nothing is leaving, no carbons are leaving at that point. So I suspect that nitrogen there is attacking in and kicking out the bromine, and what we are ending up with, and again I'm doing this because I know what I want to form, and the question has happily given me the end product, and you'll often see this, okay, that they'll give you the end product, so you need to try and work towards it. So now I've got 1, 2, 3 from the 1,3-dibromopropane, 1, 2, the nitrogen, which is positive, that's where the carbocation comes from, and 2 bits sticking up like that. Okay, it has 15 carbons, 6, 7, 8, 9, 10, 11, 12, 30, oh gosh, does it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Have I missed a bit? Yes. Yes, on one side there are supposed to be 3 carbons. So 1, 2, 3, and down. Okay, so that's where I went wrong. So it does have the right number of carbons. In terms of hydrogens, it would have 1, 2, 3, 4, 5, nothing there, nothing there, nothing there, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Yeah, I mean, I'm fitting this, and it's got the 2 nitrogens there, so I fitted all that data, and I put this together by firstly looking at the end product and seeing where I need to get to, and then thinking, well, they've already kind of introduced me to this idea up here. These questions, these organic questions, typically build, and they've shown me, they've given me a clue on the previous bit about what's going to happen here. So I know that the two ends, the two nitrogens perhaps, are going to attack the two ends. So I've got compound cation M. If I heat it at 200 degrees C, it generates CH3Br and compound N. CH3Br and compound N. Right, well, somehow I've got to get rid of one of these methyl groups, right? So looking at the product, there's only one methyl group hanging off that nitrogen. So let us presume that, and again, I'm not going to draw the whole thing because I can't be bothered. 1, 2, 3. So we've got the nitrogen here. 1, 2, 3 hydrogens. 1, 2, 3 hydrogens. Let's say that bromine comes in, attacks that carbon. Now you might say, why is it going to attack that carbon? Well, actually it's next to this nitrogen, which is very positive, so that will be pulling electron density away from it. Also, I know I want to make CH3Br, so I'm going to do that. I'm going to break that, and so compound N just ends up being 1, 2, 3, 1, 2 nitrogen with just the single one there, and then CH3Br. And actually, let's not worry about the last bit. We're not asked to, but what we're going to essentially do is then turn that cyano group into a carboxylic acid and attack that with ethanol. But yeah, as far as I know, that cyano group is still there in compound N. So now let's have a look at the mark scheme. Okay, here we go. So equation for the bromination of ethene, C3H6 plus Br2, C2H5 plus HBr. Yes, 1 mark. The Br bond is broken by light. It is a substitution reaction, yes. Smallest proportion alkane is B, absolutely. Systematic name 2-bromo 2-methylbutane, absolutely. It says allow error carried forward for correct name but wrong choice. The percentage is exactly over 12. That's what the art mark scheme says, 6/12 or 50%. Yeah, 8%, 16, 17% and 25%. Absolutely. Says half a mark per correct answer. They've done exactly what I've done here. They've worked out that this is 11.2%, sorry, more likely than it should be. This is 0.38% as likely as it should be, and therefore it is 29. They've got 29.7 because they haven't rounded. But yeah, in this competition, as long as you show you know what you're doing, they're not so fussed about rounding errors. You'll get it marked right. 29 times more likely. So here there are 3 environments. There's 1 environment. There's 3 environments. There's 4. I've made a mistake here. Yes, because there's no environment there. Because there's no hydrogens there. So that should be 4. So that one was wrong. There were 3 environments there, and there are only 2 environments there. Yeah. Number of structural isomers of compound E, 5. That is correct. The bromine, yes, here, or in fact where that hydrogen is, because they're identical. Either one of those for 1 mark. Compound F indeed does have NHCO. Yep, so I got that right. Memantine is indeed R with the NH2 group, absolutely. And anion G is indeed the ethanoate anion. Good, good, good. I'm not as bad at this as I thought I was. There are 3 structural isomers. There is 1,1. There is 1,2. There is 2,2. Possibility of the first bromination is 3/4, and possibility of the second one is 3/7. Yes, so that is 1 mark. The second mark was for 32%. Good, good, good. There's quite a long, lengthy explanation for that. So clearly they didn't think it was an easy, but actually, yeah, 32% was the right answer. Yes, cyclopropane absolutely was the right answer, and you got 1 mark for C3H6. Yeah, C3H6 was the first mark, but that is in there. It says not propene. And that's for the reason I said that it would give the 1,2 bromination product. So I didn't fall into that trap. And it is an addition reaction. Compound I. Where have I drawn compound I? Yes, this thing with the nitrogen, the 3 things in the bromine, that was I, that's correct. And then the thing that attaches to it is indeed that is correct too. The 3 carbon atoms that came from bromo propane, yes. The 2 carbon atoms that came from ethanol, yes. I'm doing better in this than the first question. Anion K, absolutely, the negative charge on there. Compound L is indeed, that's attached to the bromine, just like we saw earlier in the question. Cation M does have that N plus, good, and the 2 methyl groups there, so that's correct. And compound N has lost that extra methyl group. Brilliant. I think I only lost 1 mark on that, and that was stupidly because I missed that. Oh, that's not bad, hey? So I think that was 37 out of 38, which I'm quite pleased with. Okay, here we go. So if we have a look here, this was the breakdown. So it says copper certificate reflecting a reasonable grasp of A-level material and the ability to apply this knowledge to a novel problem was awarded to 36% of entrants. And all you needed for that was 12 or 13 marks. Okay, that was really quite low. We felt a mark of 25 or above represented a very good achievement on the paper and showed the students were able to think their way successfully through unfamiliar material. Nearly a quarter of students were there, so 25 would have got you that. Now, not to boast, but I think I got 25 in the first paper and I got 37 out of 38 in the second paper. 62, still not the highest ever score, but I definitely would have got a Rontgenum on that one. But there you go. Hopefully, having looked through that, you can think that in 90 minutes, which is under the time I took, you could have got at least 13 marks and got yourself a copper award. Maybe some of you are thinking, actually, I can even get myself in the silver or gold. Hope that was useful, and I may, if I'm feeling brave, do the 2016 paper. Thank you.